My name's Dave Bigelow. I'm a natural hazards data scientist at Minerva. Today, I'd like to walk you guys through Minerva's approach to artificial intelligence and show you how it can be used in a few different applications, and more specifically for insurtech applications in catastrophe risk modeling and management. So first off, who are we? Minerva is a Vancouver, Canada-based company. We deliver explainable cognitive AI solutions and geospatial analytics to solve problems in mining and natural hazards. We're a diverse team bridging the gap between cognitive AI research, practical geospatial applications. Our team's made up of geoscientists, AI researchers, software developers, and geospatial analysts. Collectively, we like to refer to ourselves as knowledge engineers. And while Minerva's only been around for a couple of years, our technology has been under development for a really long time. Our founders actually started the company in the early 2000s and found that computational capacity wasn't quite there for us yet. So we've kind of had some life breathed into us in the last couple of years. Recently, we've released a series of software tools under the banner of Terra Mining AI. So it's on the left-hand side here. And that's focusing on mining stuff. And based on these successes and using our domain agnostic tool, we're now expanding verticals to apply them to solve problems relating to natural hazards. We've got alpha stage prototypes built out to cover landslide, flood, and wildfire risk. And now we're looking to expand to other perils and build the products out into turnkey solutions for the insurance sector. So what tech-based solution do we offer? Minerva's cognitive AI is a bit different from the conventional way that most of us usually think about AI. And it's distinctly different from what we just heard about from Brian at Zesty. And that is that we're attempting to train the computer to think and reason like human experts. And we've found that in many ML applications, geoscience is relatively data starved. We don't have access to huge landslide and flood databases that we can train neural networks on. And instead, what Minerva does is we offer tools and support for our clients to develop expert-based conceptual models using knowledge graphs that you can use to describe a particular domain in words instead of numbers. So once defined, we use this information to apply our reasoning engine, which we call the reasoner. And the reasoner allows us to make comparisons of similarity between various physical entities, leveraging the power of the knowledge graph to compile various different data sets and make decisions about them. So decisions that people actually care about. On top of that, since we're not using black box systems, the solutions presented by our workflow are completely explainable. So you can audit the results and drill down into some of the reasoning driving the reasoning behind the scores that are assigned to different buildings. Now that's all well and good, but you might also ask, what does it actually do? Let me jump ahead. What does it actually do? So how does our technology actually apply to natural hazard, and what's the problem we're solving? Our team realized that in much the same way that you can use our tools to look for, say, a gold deposit in mining or mineral exploration, you can also look for example, houses that are at high risk of flooding or are likely to get hit by a landslide or are likely to get engulfed by flames in a wildfire. In short, catastrophe risk modeling is really complex, and limited data leads to a need for expert judgment oftentimes, which is very difficult to scale. Minerva provides the tools needed to apply our cognitive AI workflow that mimics expert reasoning, and this empowers users to make informed decisions about natural hazards with complex geospatial data and other information. So some of the industries that we serve right now are property and casualty insurance underwriting to compare different properties in terms of their flood risk. This can happen more quickly and more consistently using our approach, as opposed to just leaving it to an individual who might have some biased conclusions there. For reinsurers, Gaia can help by providing explainable risk assessments that integrate a variety of data sets. And data stored in the knowledge graph allows us to provide richer geospatial analytics than traditional tabular databases. In real estate, the explainable similarity scores can help connect investors with the right properties and also help them understand their exposure to natural hazards. And finally, linear infrastructure operators, some things like power lines and pipelines need to understand which segment of their line is most at risk of generating or being affected by wildfires. So now you have a bit of a sense of what we're doing, but what's the big deal? Why are knowledge graphs useful, and why are they important? Here you can see a bit of satellite imagery, which with a few different data sets overlain. But when you look at that image, your mind actually constructs models to make sense of it by linking with what you see with what we already know about the domain. For example, we don't just see colors, we can see a building there, and it looks like these guys have a pool in the backyard. But we can also start to fill in some of the other details about the parts of that building, like the roof. Maybe we can infer from the imagery or from the customer that the roof is made up of a particular material, and that it also has a skylight and a particular geometry. These are all things that, similar to what Brian was saying, that we can pull out from the data sets. But that's not really what Minerva is offering. And so taking this idea even further, we can start to leverage information about the occupant and the age and income, or you can look at the building's watershed, which can have a particular surface area or a land cover material to see how susceptible it is to flooding. And finally, you can look at the area around that building to see how deep the water is forecasted to be, or what the slope is, based on different CAT models or terrain models that we have available. And so as I was saying, many of these elements can be identified using computer vision tools and algorithms that are applied to satellite imagery from providers much like Zesty. But some can also come from other geospatial data sources. And it sounds like Zesty's got a lot of that going as well. But as you can imagine, this flood risk knowledge graph I'm showing here can get really complicated really quickly. And this is where Minerva's knowledge engineering comes in. What we do is we offer a tool to help you structure all of that geospatial data so that it can make inferences about the property in much the same way that your brain can. So moving on to some of the benefits of knowledge graphs, that's kind of how they work, but what's the point of using them? One of the best parts of it is that it allows you to encode expert knowledge in the computer so that the information can be used by a reasoning engine to make inferences about the data. Another great thing is that they're extremely flexible. Storing your data in a knowledge graph allows you to incorporate both quantitative and qualitative data, which is super handy for catering your product to an individual client. I already alluded to this previously, but knowledge graphs make a really rich data storage format. And one of the things we like to say around Minerva is that data turns into knowledge when it's placed in context. Knowledge graphs provide that context and increase the value of your data. On top of that, I want to make it clear that we're not really reinventing the wheel here. Instead, we're providing our clients with the tools to apply established scientific approaches and heuristics to come up with expert-based solutions across a wide area quickly. So really, we're just standardizing that process, and we're offering an interface for you to define that data and those models, and then to implement them for you as well. Finally, another big benefit, or not quite finally, but another big benefit is that our results are completely transparent. So we pride ourselves on the explainability of our AI system. Scoring system's clearly laid out with no secrets buried inside some sort of black box that you don't really know what's driving the score that you're delivered. And finally, I should note that knowledge graphs are widely used, but you may not know it. In fact, every time you do a Google search, for example, you're making use of their knowledge graph tool as they're using context of who you are, where you search for it, and how you search for it to deliver customized results in that search bar. A lot of NLP applications like Amazon Alexa and Siri are using knowledge graphs to make inferences about the questions you ask them in order to answer in the best way possible. So now that I've hopefully convinced you on the benefits of knowledge graphs, how do we do it? What does Minerva actually do? So we've got this 5-step process. We start by working with our clients to build out a knowledge graph. We call this knowledge engineering. And we'll look at all the data they want to use and start to develop a model for how those component parts interact. Next, what we do is we integrate all of the relevant data sets that are available. So we'll go to CAT model vendors and open data sources and reach out to whoever we can in order to find the best data to solve a particular problem. And then we'll align that data with the structure of the knowledge graph to put everything into context, so to speak. Next, we go to work with the experts and using our software tool to capture their knowledge and define which are the important attributes that matter for the peril being modeled. And this is one of the places where you can start to implement data-driven solutions if you have if you do have those inventories, if you have a flood inventory or a loss inventory from wildfire, you can start to make these weights and the important attributes. You can start to account for those using data as opposed to expert opinion. But that's just one of the options here. And with all that done, we then apply the information with our reasoner to compare between the data and themselves or with predefined expert models. And the reasoner results are then delivered in various different ways, but we like to display them in a web dashboard so you can interact with it and drill down to understand some of the scores that we're developing. So this is an example of a flood risk dashboard mockup that we've put together for one of our pilot projects. Here we're comparing the gray house in the crosshairs there with all of the other houses in the portfolio in terms of flood risk. So this particular result uses more than 25 different geospatial data sets, which are listed on the left-hand side of the screen, to come up with the reasoner flood similarity score. On the bottom left here, we've got the details on the property of interest. In this case, it's 123 Oak Avenue. It's just a nice fake name for you. As well as some of the important reasoner parameters and property attributes that went into driving this model. On the right-hand side, you can see you've got the reasoner score, which shows the similarity of this property with all of the other properties in a portfolio. And the closest match is shown at the bottom right. So these results can be used to extract actionable insight from your data by, so for example, an insurance underwriter might have a customer looking for flood insurance whose home sounds really similar to one that they wrote a few weeks ago. They can then search their local knowledge graph network to compare just how similar this new property is to the one that they wrote a few weeks ago, which allows them to price their premiums a little bit more consistently and more quickly. While this is pretty similar to the typical scoring system that most CAT model vendors will provide, remember that the data are stored in a knowledge graph, so they're placed in context, and you can drill down into the results by clicking the Match Report button to get detailed explanations for exactly why 123 Oak Avenue is similar to 456 Main Street, in terms of flood risk, I should say. So drilling a little bit deeper into the data, you can see that we're matching on a fairly granular level because of the richness that knowledge graph format provides, and we can present that to the user in a fairly user-friendly interface. Here you can see the buildings themselves are an 87% match, while the building watersheds are a 42% match. So here you can see how there's various different physical entities that relate to flood risk, and you can see how all these sort of component parts sum up to produce the final match score, or reasoner score, I should say. A typical data set that we like to include in our models is the CAT model outputs that you can get from typical vendors. So oftentimes you'll get a flood score. So even in the previous presentation, there's the Z flood score, the Z fire score. These are helpful because insurers are typically already using these scores in their pricing, and our software allows the user to assign weights to them and allow them to combine these data sets with other geospatial data. In this case, you can see one of the properties has a flood score of 2, while the other one has a flood score of 1. And since those scores are relatively close together, the reasoner sees this as a partial match. What's important to note is that we're not really replacing the traditional CAT modeling approach, as these tools are produced by armies of PhDs that are quite frankly beyond our level in terms of knowledge. In our case, what we're doing is we're enhancing those outputs by putting them into context and helping users interpret their outputs. In addition to CAT model scores, we can also include many other different properties that hydrology and flood modeling experts use to evaluate risk to a property. In this case for flood, but the same can be said of wildfire and landslide at this time, such as buildings' distance to water course, or the related watershed surface area, or even the land cover material, sort of like we showed in that satellite imagery earlier. So To close, I just want to summarize what Minerva is all about. We deliver cognitive AI solutions and harmonize geospatial analytics to solve complex problems in CAT modeling and risk management. Our domain agnostic technology has been proven in mining and mineral exploration, and it's enabled this great rapid adoption of cognitive AI for a number of different clients for numerous different applications. So we're really excited to keep pushing into the natural hazard space, and we're looking forward to applying our workflow to many different new hazards.
Guri has asked, are your solutions geared towards insurance underwriting or claims?
Right now, it would be towards underwriting because we're not collecting data after the fact. So right now, we're just collecting any sort of open data sources and satellite imagery beforehand to support underwriters as opposed to after the fact. So yeah, Short answer, underwriting.
Yeah. Sudi has asked, thank you so much. Could you please explain the 5-step process and how effective it is?
Sure. 5-step process being the way we sort of integrate data into our cognitive AI process. For sure. So the first step is to build your knowledge graph. So what you're doing there is really just structuring the information and structuring domain knowledge in one place. There's a lot of different words that people use for knowledge graphs. There's ontology and semantic network and things like that. We try to keep it simple by just referring to them as knowledge graphs. But yeah, so the first step is to just structure everything, or basically what you do is you try to structure everything that an expert knows about, say, flood risk. And then once you've sort of defined those entities, then you align numerous different data sets to that data standard, which allows you to sort of view it all in one place. And then the next step is to take the expert's knowledge about the domain and say, okay, I know what constitutes a house that's at high risk of flooding, so let's start to define those attributes. And then the next step is to throw that knowledge as well as the data at the reasoner, and then develop some scores of similarity between either the entities themselves. So whether you've got various different houses, you can say house A is similar to house B. Or alternatively, you can say house A is similar to my conceptual model of what an ideal, or ideal isn't the right word, but an idealized house that would be at high risk of flood damage. And then finally, the last step is just to display the results. Not really a step so much as just a phase in the workflow.
Diego has asked, what do you think are the most useful skill sets for a data analyst or scientist to succeed in the industry and in Minerva specifically?
To succeed in the industry specifically, a lot of the most useful things that we've found is people with experience in semantics and with who have worked with data in a graph format. That's really important, but also just having domain expertise is really helpful. So knowing about whether you're a landslides expert or a floods expert, those are also really helpful. For us, geospatial data is pretty huge. So that's another skill to be able to work with geospatial data is really important.
Nice.
I think it's out of almost a PNC sort of field.
Erica said, for rare events, how does your platform deal with sparse data in training your knowledge graphs?
Yeah, so that's a great question. That's kind of the whole point, is that you can generate knowledge graphs from data if you have them. But what we try to do is we're not so much data driven. What we do is we'll go and interview experts in order to define those knowledge graphs. Basically, like you just assert things. So rather than deriving that from sparse data, which is oftentimes can produce spurious results, what we're doing is talking to experts and saying, look, how do these component parts interact? So really, we're just completely avoiding the whole sparse data because the knowledge graphs are not trained on data.